Hi, everyone. Good evening. So I'll be taking today's session. My name is Vangelis Oden. I am a data and machine intelligence engineer with Indicina Technologies Limited in Lagos, Nigeria. And today's session is applied classification in machine learning, identifying classification problems, learning industry use cases, avoiding pitfalls when applying classification algorithms. And basically, I'll be trying to explain all of this to you and how you can also start out with thinking classification problems for your particular industry. The explanations I'll be giving will be quite simple or easy for anybody of any background, of any level of expertise to understand. So, yeah, just come with me. All right, so the outline, I'll start with an introduction where I'll try to introduce you to the concept of classification and classification in general. Then I'll give you an analogy and problem statement, what we'll classify as classification. And then we'll go further into classification to understand the various types and the various methods that we can use. And then I will talk about some solutions, and then machine learning in practice generally, and finally conclude. Then you can ask me all the questions you would like to ask. So an introduction. A quote, "By their data, you shall know who they are." In biology, classification is simply the arrangement of animals and plants in groups based on their observed similarities. So this includes the kingdom that the animal belongs to. For instance, cats and lions belong to the same kingdom, but they're separate entities, each on their own. And then we have the phylum, we have the division in plants and class order, we have the family, we have the genus, and we have the species. So these are deep levels. I don't know, for those of you who did biology, you would always remember, I always picture this tree of the parent class, then other classes inheriting and branching out to their various subclasses, subclasses. So simply put, classification is a category into which something is put. So we would generalize today and say, oh, because a person has hair, because a person has hips, because a person looks in a particular way, and etc., we would say, okay, yes, this is a lady. And if a person looks in another way with broader chests and some other physical quantities, we would say this person belongs to the masculine class. So we have two classes, the lady and the male. We then try to find out the properties that make for a lady and the properties that make for a male. This is your simple definition of classification, trying to put things into buckets, into brackets, into groups, into classes, into categories. And so you'll hear me say some of these words or use some of these words interchangeably to talk about classification. Don't worry, I mean the same thing. So I'm talking about class, group, category, rank, bracket, and type. And yeah, some other words that I've not included yet. But wherever, if you have any issues, just send me a mail or tweet at me. Right. So in classification, many of the times what we're trying to do is, or some of the times what we're trying to do is detect a class in an image, in an object, in a picture we see. This is not limiting, right? But I'm just using this as an example. And sometimes we're trying to do object localization, where in an image is a particular object, where in an image is a particular item we're looking for, or in an image, what are the items that are available in that image? These are called the first method I mentioned. We're trying to figure out where something is in an image is called object localization. And the second one is called object detection, where you're trying to identify in an image what is in that image, what objects are in that image. It's called object detection. So why do we do what we do, right? We try to study how to automatically learn to make accurate predictions based on past observations. So at the beginning of the slide, I said, by the data, you shall know what a type is. So let me just go back. By the data, you shall know who they are. So we try to learn using historical data, and then using that historical data or data about any particular subject, we can then say, if this data is this part, it has this property. If this has this property, then it belongs to this class. So for instance, for the cat and the dog, how would we know a cat? How would we know a dog in an image? We would look at the properties that make it a cat: the eyes, the nose, and the mouth. And then we'll look at the properties that make for a dog: the eyes, possibly the nose and the mouth, and possibly the ears. And we can see very quickly that those two properties are not the same. In some animals, they can be similar, yes, but generally, it's seen that they will not be the same thing. So you would even notice sometimes you struggle with yourself to identify what type of maybe dog breed it is, or what type of cat breed, or possibly for some very funny looking dogs, you would try to classify them mistakenly as cats. But yeah, what we're trying to do, or what we always try to achieve, is look through the features of certain classes, or based on the problem we're solving, and then try to bucketize or put the elements or the observations we find into the various classes. Okay. So the analogy and problem statement. So what we're trying to do now is identify which of a set of categories a new observation belongs to. So we'll use one of two techniques. One is traditional programming. Traditional programming is a more dynamic approach to grouping observations using multiple logic systems. So I could say, I'll just go back a bit to this slide. So I could say, if the eyes are slant, if the nose is small, if the ears are pointed up, then it's a cat. If the snout is longer, if the tongue is longer, if the eyes are less flatter than, I'll just say less flat, and the ears can fall and rise, then it's a dog. Now, that's just a general assumption, trying to help you understand how would create traditional programming systems to do classification. So simply put, this is using multiple if statements. I just take multiple if statements and case them all together so that any input data can easily flow through to a class. If I see a new observation, I can say, if this observation relates to this particular logic statements, then it belongs to this class. If it doesn't relate to this particular logic statements, then it belongs to another class. Now you can see already that this can become a very hard problem, because yes, in this slide, I mentioned just about 4 or 5 properties. 4 or 5 properties in the image that could help determine if it's a cat or it's a dog. Now, if for any reason this dog or the cat is backing the person that took the picture, and I have access to that picture, you can see very rapidly that I can see an eye, I can see a nose, I can see a tongue, I could possibly see an ear. Now, my traditional rules would very quickly fail, right? So this is what helped a lot of people, or helped us move from a more systemic approach of hard coding everything to a system where we allow the computer understand what features lead to predicting a particular class. So for the traditional programming, we have a computer. We'll give the computer the data. So we'll give the computer the data, the cats and the dogs, and then we'll give it some rules and tell it, if this rule is met, send it, this image belongs to this class. If that rule is not met, then send it to another class. And then from that, our computer will take in new examples and try to give us an output. So this is the problem now. The problem is the rules. We're giving it rules on how it's supposed to understand data. And we can see that as the data increases, as the data becomes a lot different varieties of images of cats and dogs that are not looking at us, that are upside down, that are sleeping, we may start to have issues if our rules are not robust enough. But can we really have robust rules? How robust is robust enough? So that's where we have machine learning. Now with machine learning, all I can tell the computer is, I'm not going to give you rules. I'm just going to give you data, and I'll tell you what each data point is. So I give you a picture of a dog, and I tell you that that is a dog. I give a picture of a cat, and I tell you that's a cat. And then from there, I want you to learn the representations that make an image a dog and the representations that make an image a cat. And with that, develop your own rules, right? So we teach a computer in machine learning, we teach a computer how to learn. We don't teach it what to do. We teach it how to learn so that it then knows what to do, right? So you can see now it becomes very interesting. I don't have to spend my time coding if there's an ear, if there is an eye, if there is a nose, if there is a mouth, if there are legs, if there is hair, if the hair is scanty, if the hair is brushed, I don't have to spend my time coding all of that, because when you start coding some of those things, you'll see very largely how large some of those scripts can get. And yeah. However, not to throw away traditional programming. Traditional programming actually, in a lot of cases, can help to build the baselines for which machine learning would come on board. As a matter of fact, I was speaking yesterday, and I said, if your problem cannot be thought of in a traditional programming setting, then most likely you cannot do that in a machine learning setting. A lot of people just think, oh, okay, every problem, since we're talking about machine learning now, we're just going to jump on machine learning and just start doing machine learning. No, if your problem cannot be thought of as a traditional programming problem, it cannot be thought of as a machine learning problem. So I just explained now the problem of trying to classify an image as either a cat or a dog. I've been able to show you how I would write the traditional programming logic for identifying the two classes, and I am now shifting and telling you, okay, well, since I've seen that I can do that with traditional programming, I can now do it with machine learning, right? So what is machine learning classification then? First of all, we need to understand what learning is before we can understand what machine learning classification is. Learning is any process, like I've explained, by which a system improves performance from experience. So I take a lot of, I give a computer a lot of data and I tell it, learn the rules for which I have this data and I have this output, the output or the names of the data. And the computer learns that. And it now has to find a way of improving its learning experience from new data. After it has learned the rules, I then give it some new data that it probably didn't learn from and tell it, oh yeah, now you have gone to class. This is an exam. What image is this? And it's able to tell me based on what I have learned, based on how I learned, this is a cat or this is a dog. So machine learning is the study of algorithms that improve their performance at some task T with experience E. So a well-defined learning task is given by this three statements: improving their performance at some task T with experience E. So when do we use machine learning? We use machine learning when human expertise does not exist, right? It's an experimental system. It's an experimental system that has the probability or possibility of performing really, really good or performing really, really bad. But we know that sometimes there might be no expertise, or that the amount of information we have to process is way more than a human being can actually sit down, or will take too much time to process. We then give those kind of data or problems to a machine learning algorithm or machine learning system, combination of systems, to try to learn representations within data, find patterns, and help achieve what we're trying to achieve. Another reason or time when we get to use machine learning is when humans can't explain their expertise. So I was born and I learned how to speak my language from an early age, but I never really went to school to understand how to speak it. I never really was sat down to be taught the syntaxes of how my language evolved and grew. I knew how to speak my language. After some time, I could respond and reply to my mom when she's talking. How was I able to do that? My brain was able to find patterns in how, in the words that were spoken, how they were spoken, and the syntaxes that were spoken. So with that, it then was able to it was able to connect and tell me a word to say and how to say it whenever I needed to say it in my language. I cannot explain that expertise to you. I cannot explain why and how I'm able to understand the language. But then, yeah, if I want to train a system to understand, how do I teach it that, oh, if you see this word, convert it to this word. If you see this word, convert it to this word. You can rapidly see that for Igbo example, I will have to learn all the words in Igbo to be able to translate them to English words. So that's a very, very huge problem. I have to find a way to give a machine learning algorithm that problem to solve. So models are based on huge amounts of data. When you are in industry, you would find that there is tons and tons of data running in terabytes, running in exabytes, as a matter of fact. And many of that data is useless to a lot of people because they do not understand the techniques, the methods that could draw insights from all of that data. So because of how much data we have available as images, as text, as emails, as audio, as tabular data, we have to find some kind of system to put all of that data into and find a way of drawing insights or identifying patterns within them. So when do we use machine learning classification, right? Machine learning classification is one of the most used methods in industry. And I'm sure you might have, but even if you haven't, you may get to see regression And regression is basically trying to use past data to develop a system that once I have new data points, I can always know, I can always fit. So in regression, we're not trying to find out what class something belongs to. We're trying to just know, okay, for any input, what could be a continuous valued output. So for instance, I want to predict the price of a car. I would give input features for what a car probably will, what it capably is. For instance, the wheelbase, how old the car is, the size of the car, length and breadth and height, possibly the amount of the size of the fuel tank. And with all of those, I can develop some kind of model to predict a real valued output that's a continuous output of how much exactly the price would be. But in classification, we're not trying to predict how we cannot try to predict how much the price of a car would be. We would want to predict maybe the range of prices that a car could fit into, a bucket of prices, and say, okay, for instance, I would say my classes at the end are a car belongs to the two classes, lower than 500,000 and above 500,000. I would then get features, those same features, and try to predict what bucket the price of the car should fall into. But in regression, I will be trying to predict the exact amount that car should be sold for, right? So you can see the clear difference between both of them. In one, I'm trying to, classification on the left, I'm trying to predict what class something belongs to. And in regression, I'm trying to predict a continuous valued output for a particular input, right? So when do we use machine learning classification? Machine learning classification being one of the most used, we use in recognizing patterns. And some of the applications involve identifying object instances of a specific class in a digital image. So we can check for facial identities or facial expressions. So you can use your device today, your mobile device, and just look at the screen and it can unlock itself. How does that happen? It's basically your system understanding that that's your face. And we have facial expression systems that now can tell what expression you have on your face. If you're sad, if you're happy, if you're just indifferent. And with all of that, you can link you can begin linking these systems to recommendation engines or systems where someone is looking at his phone and is quite sad, and a recommendation pops up for a nice musical piece for the person, and he's able to listen to it and gets maybe a little bit lighthearted. So yeah, facial expressions. We have handwriting or spoken words, where you try to, a machine learning algorithm tries to understand what the letters you're writing using your stylus on a screen. You just write, and the machine learning algorithm is able to understand this is what you wrote, right? So it doesn't matter if you're a doctor with your handwriting or whatever you are. As long as you can write, the machine learning algorithm is able to pick out what you wrote and translate it to maybe whatever it is that you really need to say. So yeah, in keyboard typing, for people who don't like to use keyboards, they can just write and have their handwriting converted for them. Then we have medical images, where we try to identify various patterns within X-rays, brain scans, blood samples, and try to classify those into different areas, different problems that may exist. So for cancer, and this is an area, medical images is an area where a lot of advanced research is ongoing now into understanding how machine learning algorithms are able to see cancer in patients, see other underlying conditions by just looking at scans of those images, of those people rather. Then we have generating patterns. Machine learning algorithms now can generate stuff, generate text. They can generate text, they can generate images, they can generate motion, right? So if you follow the trend of applications currently, you would see that there's the new trend of called deep fakes, where someone says something or records a video doing or saying something, and they can rapidly put another person's face on that person's image, and it looks like it's another person that's talking or performing the action. This is a very troublesome field as we're seeing it, but yeah, there's a lot of good that can also come out of it. Text generation too, when you're typing on your phone, if you notice sometimes there are recommendations for words that you can just tap on and select as the next possible word that you would have wanted to say. And a machine doesn't just sit down and guess those words for you. It actually tries to learn how you've been conversing over the years. And with that, it's able to learn the words that you frequently use given a sequence of text, and with that predict for you what particular word you would want to use, making it easier for you to just tap on the word without having to type out the word you need to type out. So yeah, the same. Likewise, creating recommendations for content. I don't know, the other day I went on YouTube and I got a recommendation for something I don't know why they would give that kind of recommendation for, but yes, I was surprised at the content. I wasn't surprised that they sent it to me. It would have been obvious that they had used some kind of recommendation classification system to understand my behavior over the past couple of years or months, and then with that being able to predict what I would possibly like to watch. And yeah, I actually did like the content that they recommended for me. Yeah. So the next is recognizing anomalies. Now, these applications involve identifying occurrences out of the ordinary. So unusual credit and debit transactions. I don't know how many of you have possibly gone to withdraw money and you were told you couldn't withdraw money. You probably had to verify who you are, or go to a more frequently used ATM machine before you could withdraw that money. That's basically anomaly detection. So every human being, all of us, as we move today, we have patterns in which we move. We have patterns in which we act. We have specific places we go to, specific places we try to do certain things. So for instance, I'm in Lagos today, and I've been in Lagos for the past 1 year, 2 years, and I'm making withdrawals in Lagos. And for some reason, I find myself in Berlin and I'm making a transaction. My bank almost would be able to acknowledge that that's an anomaly. I have not been to Germany. Why would I be making transactions in Germany? So they can very quickly shut down that operation. So if for any reason I wasn't the one that was making the transaction, but someone from somewhere was able to hack me and get to use my information to make that transaction, I've been saved, right? So this is one application of machine learning, classification, that is highly being used, yes, in credit and fraud transactions basically, to identify. And yeah, of course, if it's not a fraud transaction, you can always just call your bank and tell them, no, I'm actually the one trying to make the transaction, and they can release it. Now the machine gets to learn that you are in Germany and you're trying to make that kind of transaction. So it won't flag it anymore as you keep making transactions. But if for any reason you up from Germany and you're in Australia in a couple more in a couple more weeks, then they get to flag that one too, because but now it won't be as severe as the previous, because the machine has now understood that you have started moving, you've started traveling, right? So the next is unusual patterns of sensor readings in industrial machines. Industrial machines many times run for months on months on months without stopping, and only for preventive or prescriptive maintenance do the engineers stop them sometimes. But sometimes between maintenance, a machine can fail, a machine can have issues. How would you know when a machine can have or will have issues? With recognizing anomalies, if you have a machine learning algorithm that really looks at the nitty-gritty small details that you would overlook, it can tell you, oh, this machine is going to fail, and it's going to fail this particular day. It's going to fail this particular time, and it's going to fail, in the words of Trump, bigly. So you can then stop at that point and do a maintenance at that point without waiting for the next maintenance cycle. So this is how we would use machine learning in some of those industries. So you would see in oil and gas industries, in plants, a lot of plants, power industries, processing industries, you would need machine learning to help with some of those things. Then you have the final use, prediction. This involves forecasting an occurrence, usually time dependent. Now, this is not that much of classification, but yeah, it's basically machine learning forecasting, where you try to take stock prices and predict what they would be in a particular hour, in a particular day, in a particular time frame, and with that you can make your case for a sale or a buy, and basically manipulate the market as you would want to, in and out of the market. You could predict a player's peak, how long a player is going to last in the market, so we can know if Ronaldo is going to survive the next 5 years in peak performance. And with that, I can help negotiate contract deals for him. And yep, the companies would be willing to sign up or basically work with him on contract deals based on off the data of my analysis on his peak performance. So these are a lot of methods we would look at, but these methods are not exhaustive, right? I'm just listing only a few. I can't go over all of them because daily there are new methods. Daily there are new methods that come up that we try to look at and see, okay, how can machine learning and classification be used for these problems? So we have the methods. To be able to build systems that can solve the above problems that we have just stated, one must be able to understand various computational and machine learning methods and the types of data each method is most proficient with solving. So we have two basic methods, and I'm talking now just for classification. We have more methods when it comes to a lot more problems out there. But when it comes to classification, we have two methods where we have the statistical machine learning classification. And in that method, we're just using statistical methods, logistic regression, k-nearest neighbors, support vector machines, to try to classify data into two or more classes. And then the other method is the deep neural networks, where we adapt methods of neural functions to predict what class a particular input data belongs to. I'll explain this a little bit more. So in statistical machine learning methods like logistic regression, naive Bayes, etc., we rely heavily on structured data. That's data in tables to learn relationships. And you can see in the representations there, we're just trying to create a decision line between data of between two or more data clusters. We're trying to say if the data belongs to this cluster of points, because of course we know most cats would look alike, right? Most cats would look alike. Most dogs would look alike. They would just have variances in height and muscles and the particular breeds they are. But they would almost all have something in common that makes them dogs. Same thing with the cats. They would always have something in common that makes them the cats. So all of the red data points, let's say they belong to cats, and all of the blue data points belong to dogs. And what we're trying to do is just draw, when we're trying to learn using machine learning, we're just trying to develop or decide on this line here, that's the diagonal line, that separates both of the classes, so that when we come with a new class, when we come with a new image rather, we can identify where that image falls in and just generalize the class based on where the image falls. So for k-nearest neighbors, we're trying to find, okay, if this class is here, what are the neighbors surrounding that class? And if we find the majority of the neighbors surrounding it belong to the dog class, then we say, okay, if you're surrounded by dogs, then you're a dog. If you are surrounded by cats, then you're a cat. If you're surrounded by thieves, then you're a thief, right? And and the other method, the decision trees or classification trees, just tries to separate the data based on some decision. So it takes a feature and says, if the person has long hair, then it's a male. If the person has short hair, then it's a female. And then with that tree or with that tree classification, it's able to break down further. So yes, I may start with a beginning classification, but I may not end with that same classification from the beginning, right? So that is basically statistical methods. And each of these methods is trying to learn either, for the classification tree, is trying to learn a graph flow such that if I give it input data, all it just asks is this data, does this data have this property? Yes, go this way. Does it have this property? No, go this way. And in support vector machines, and logistic regression, I'm trying to learn a weight, just a couple of weights that would help me predict what a new input would be. For k-nearest neighbors, I'm trying to understand what is the family? What is the family for any data point? So that when I have new data points, I can just look at the surrounding and say, okay, because it has this surrounding, it belongs to this class. And then for deep learning methods like convolutional neural networks, if you've not heard of them, now you've heard of them. Convolutional neural networks, recurrent neural networks, these systems rely heavily on unstructured data. So we have before the hype of AI and all of that, most of the techniques we had access to were the statistical techniques, because most data was stored and is still being stored in tabular forms, that's as columns and rows. If data is being stored as columns and rows, most statistical techniques can solve them. That's, logistic regression and support vector machines and the others can solve those kind of data points. However, when you have data as images, data as sound, data as video, you're now talking in more than just rows and columns. You're talking about color, you're talking about pitch, you're talking about amplitude and all of that. Those type of data points cannot fit into a linear classification algorithm that just tries to separate two data points linearly, right? So we need more advanced techniques that can identify each of the data points and say, okay, based on what I've identified, I think this image or this sound or this video belongs to this particular class, right? Deep neural networks are or deep learning is a more advanced method and is really, really data hungry. So if I'm going to feed it data to learn, then I have to feed it a lot of data, right? So our solutions now, where I work, we provide data services to lenders who may or may not have the capacity to understand their customers, but want to have or leverage advanced methodologies in identifying their customers and other data that they possess. So what we do is we go to a lender and we say, hi, do you want to know who your customers are? Do you want to know if a customer is possibly going to default on a loan? Do you want to know what type of loan a customer could have access to, and not necessarily just decline him for every loan application he makes because he doesn't meet some certain criteria? And the lender is like, oh yeah, let me know what you can do. So we take your data and we build a credit probability of default model. And what we're trying to say in that is, will a customer repay a particular loan or not if he applies for that loan, based on how people have been interacting with that particular loan portfolio you have. So we can just use historical data and try to assume and say, okay, if this customer has this, if this customer does this, if this customer comes from this place, if this customer does has this, works in this place, does this, has that, and all of those data points, we put all of them together. And instead of writing if the customer to determine the output, we just tell the machine learning algorithm, come learn how this customer would possibly default or will not default. And it gets to learn that. And we now just play around with tweaking it to understand how much risk we want to bear in how the machine learning algorithm is able to predict for a customer. And with that, we can now ship that solution and say, okay, yep. So a new customer comes to apply for a loan, and we tell the machine learning algorithm, we're like, hey, from what you've learned, can this customer repay this loan? And the customer say, and the machine says, oh yes, he can repay. And we're like, okay, fine, come. Let's discuss. And we then discuss with them certain things about the loan and all of that. And the customer is happy, he takes his loan and he goes home, and we're happy too, because we can trust that a machine learning algorithm with a certain percentage of accuracy or confidence was able to say this person, he trusts that this person can pay the loan. And then we say, oh yeah, you know what, we were able to do the analysis, but yeah, it's not, I'm giving you the high level of it, right? I'm giving you the high level of it, but yeah, there's a lot of deep work that goes into building these systems, the type of data that goes in there, the type of data that comes out of there, and the types of decisions that have to still be made from what algorithm is able to predict. Then we have fraudulent statement of transactions, where users upload fake bank statements or wrong bank statements so that they can try to game our systems and collect a loan and disappear. And yeah, now we're fairly good at finding them. So you think you're going to come and fraud the bank or whoever our lender is, and the lender cries to us and is like, no, I need help. And we just come in and using previous how customers have been defrauding banks before using fake bank statements, we're able to build those AI solutions that then monitor for this kind of occurrences. And with that, we're able to say, oh yeah, we found one person. And then we invite you and say, oh yeah, your loan is ready. You can come take your loan. And you come and we have the police waiting for you. And yeah, we've been able to develop this kind of systems now, and they're currently working for a lot of customers. Then we have the user income classification, where we try to group customers into how much they possibly earn and find out the risk involved with maybe lending to a particular group of customers, earning a particular amount of money, and how we can develop solutions around giving them the best facility for because it's basically about them. We want to be able to give them the best facility that will not stress them, but will allow them enjoy the loan as well as payback on time, right? Because we need the money back. Then we have credit facility recommendation. This is in tie with the previous, and all of the others, of course, the credit probability of default. So in previous times, you would go to a bank and you would apply for a loan, and the bank would possibly tell you, no, based on what we're seeing, we don't think you can handle this loan. So sorry, goodbye. And most likely you will not be able to apply for another loan till at least 3 months, because of the type of documents that the banks will check. But now we're able to see that, oh, we've been pushing out a lot of people who could actually have taken loans, but maybe not just the amounts that they applied for. And so we tell them, oh, okay, fine, you're applying for maybe 500,000. We don't think you can take 500,000 and pay back in the expected time and without stress to your finances, right? We care about you, so why don't you come back and take 200,000? And many of the times you would see that, oh, customers could actually do with the 200,000. Maybe it helps to ease the particular need for the loan at the exact time, and are able to now plan within that amount of money. And we're still able to make some money. So now if we were rejecting maybe 80 customers out of 100 on a daily basis, now we can accept we'll just reject about 20 or maybe 30, and the rest we're able to account for based on the risk and the credit facility recommendations we can build, right? There are other areas that we're looking at, we're researching continuously. I am leading the machine intelligence team on research and all the applications, where data can come from, and how we can expand solutions to other types of lenders. Depends on what they need, based on what they need and the type of data they have available to identify what their customers are, who their customers are, where their customers are. So how do we do all of this, right? How do we think a solution? How do we go about formulating a solution, right? We have problems. How do we get about to solving them? First, we choose a training experience. We choose the training experience. How is the model going to learn? What are we trying to achieve, right? What are we trying to achieve? How is the model going to understand learning? What do we say is good learning? What is the benchmark for learning? Then we try to choose what has to be learned. What is our target? Are we trying to learn fraudulent bank statements, or are we trying to learn who will pay back a loan or not? Are we trying to learn what credit facility someone could possibly have access to? Or in the case of the dog breed, are we trying to separate both classes of dogs and cats? Then the next is, how do we represent our target function? How do we represent our target? What makes for successful learning? Then we choose a learning algorithm to infer the target function from the experience. We then go ahead and select what method out there, out of the 1,000 machine learning methods algorithms they are. We then select a couple that belong to the same class possibly, and try to experiment which one does better at solving the particular task. We pick a good learner and try to improve how he understands the data. But one of the issues that or not issue per se, but one of the major parts of learning is the data. The data is it's the most important part of what we are trying to do. Without the data, we cannot build the systems we need. So we have to formulate our problem. How do we get our data ready? We need to get, most of the times what we do is we get historical data, because we use historical data to try to teach systems, and then use new data that will be coming in to allow the model see how it is allow the model see the new data and predict on the new data or make inference on the new data. So the historical data we have, what we now do is we try to separate it into a couple of sets, 2 sets, 3 sets, and do what we call training and testing, where we take one part of the data and we train the algorithm, and then we take another part of the data and test the algorithm. And with that, we can see, okay, if it's performing at this particular level in our systems, then if we deploy this to real world, we hope that it should perform at this same level with maybe a confidence interval we would give it. And with that, we then know when to stop teaching and when to send it out to the world. So it's similar to you going to school. You go to primary school and you learn every day. You learn, and at the end of the day, you write exams. At the end of the term, you write exams. When you write your exams are linked to how your exams try to give a picture of how you learned, of what you learned, of what you understood during the teaching, during the semester as it was going on. And with that, a teacher can say, okay, I'm confident that you can progress to the next class. Or, no, I'm not confident you can progress to the next class. You stay back one more year and we'll teach you a little bit more, maybe because you didn't understand this, some particular concepts. So that's basically what we do. That's what we do at work. We try to train the models, teach them how to understand from the data. And each time the model tries to do an exam on the testing, and we can then notice how it's able to learn. With that, we can know, okay, this model is good for shipping, go, or no, you're not good for shipping. We then try to understand what's the problem. Why are you not able to understand fully what you're supposed to be doing? We then look at the data, we then look at the model itself. Is that the right model for this problem? Is this the right data formulation for that particular model? And put the two again together and continue iterating to see if it gets better. So we generally would assume that the training and the test examples are independently drawn from the same overall distribution of data. We call this the IID, which stands for independent and identically distributed. So for instance, if I am collecting data on people or for people who are taking loans in, I'll use, for example, Lagos, I would take examples from Lagos. However, if I want to test that model, I have to test it on Lagos. I cannot take that model and go and test it on people who are taking loans in Kigali, for instance, right? It will not work. So I have to always take my data for training and also testing from the same overall distribution, right? If I'm going to take that same model somewhere else and use it and test it somewhere else, then that is a process called transfer learning. So transfer learning is basically, I train a model using a data distribution, and in trying to test it on I can take that model now and try to test it on another distribution. Transfer learning. So all I'll just do is take the model, the weights, the parameters that form the model, and try to help the parameters adapt to a new data distribution, adapt its learning to a new data distribution, and then test how that process works. So transfer learning. So there are tens of thousands of machine learning algorithms, and more still are being created. However, since we know every machine learning algorithm has 3 components, we just pick the candidate algorithms that represent our particular problem. So based on the three components below, the representation, the optimization, and the evaluation, we can then pick the particular algorithm that fits the particular problem we're trying to solve in terms of representation, how we'll optimize it, and then how we'll evaluate it. So for the representations, We choose the model that best supports our data and problem through experimentation. We have numerical functions representation, and all of this have a lot of math added with them, but I'm just going to explain high level for you. If you need the math, if you need the code and all of that, just send me a mail. I have a lot of things available, links and stuff that will help you understand many of these things in depth, many of these methods in depth. So yeah, one of the ways is we can use a numerical function like a neural network, or support vector machines to statistical techniques, or support vector machines to statistical technique, and neural networks to the basic deep learning methods. And yeah, or symbolic functions, decision trees, or rules in propositional logic. We saw decision trees earlier. Or we use instance-based functions, nearest-based, where we saw if your neighbors are dogs, it's possible that you're a dog, and case-based systems. Then we have probabilistic graphical models, which have naive Bayes and the Bayesian networks. All of these methods, these are not the only methods under each of the classes, but yes, these are the primary ones we first start looking at before we try to advance to deeper, bigger, larger methods. So that's for the model representations. For the model optimizations, now you've selected a method. So let's say we selected a neural network model, and we try to help the model improve. How do we help the model improve? We need to find an optimization technique, right? An optimization technique just takes the learning and tries to help the model find the best solution to how it's able to interpret data. So we have gradient descent. Gradient descent is an optimization technique that you, and under gradient descent, we have backpropagation and perceptron. We have dynamic programming, HMM learning, PCFG learning. Again, all of this, I have materials on all of them and what they do exactly. If you would want to learn, just send me an email. We have divide and conquer, decision tree induction, rule learning. So decision tree, we saw decision trees. Then we have evolutionary computation, genetic algorithms, GNAs, and then neuroevolution. So we take, for example, the neural network. We picked a neural network and we said, okay, fine. We would want to optimize a neural network. The method we would use for optimizing a neural network would be the backpropagation. We use backpropagation, and backpropagation tries to optimize a system of a neural system of weights to get the best weights that could solve a particular problem. Now we've been able to optimize our algorithms. How do we know the algorithm has learned or the model has learned well? We go to the evaluation part, and in the evaluation we understand what the models are doing, and we try to understand how they learned. So we use accuracy. We use metrics like accuracy, like precision and recall, like squared error. Squared error, you would find that in regression tasks. KL divergence, you would find that in anomaly detection tasks. Accuracy, you would find that in most classification tasks. Accuracy, precision, and recall in most classification tasks. And what we basically try to do in accuracy is see how much. So it's like, let's take the example of going to school, and you learned for a whole semester, and you wrote an exam, and you had 10 questions. You were given 10 questions in the exam. Ordinarily, your lecturer would have the marking scheme, and the marking scheme represents what are the true answers for those questions. Now, when you answer the questions in the exam, the lecturer then tries to compare your answers with his and marks off the ones you had wrong, and corrects the ones you had correct. So with that, he's able to tell, out of the 10 questions you answered, you got you got 80, you got 8 over 10 of those questions. 8 over 10 of those questions are based on my marking scheme, based on the true answers I have on my marking scheme. So you got 8 over 10. And if you got 8 over 10, if I'm to move that to a percentage, that means you had 80%. So if I teach a model and the model, or I help a model learn and it's able to understand 80% accuracy, I can decide based on my business metrics, is 80% accuracy okay for this particular problem? Can I send 80% accuracy out now and then try to improve and later maybe get up to 90% accuracy and replace the 80% model that was out there? Can I do that, or do I wait and continue improving the model's learning till it gets to about 90% accuracy? Then I deploy. Now, all what I just stated is no mean feat. It's almost difficult to do some of these things or perform some of these miracles in a very short possible time. You would have to do a lot of research. You would have to do a lot of data wrangling, a lot of tuning and turning before you can possibly get the models to that level of accuracy, or that level of confidence that you can say, oh, I'll send it out there. So we ordinarily try to avoid models with very low performances on tasks, because if you send out a model with 50% accuracy, how do you, I mean, that's like saying I could do the job. I could have just sat down and done the job. What's the point spending so much time, resources, and money and sending a 50% accuracy model out there? So yeah, we try to always get really good accuracies, and try to also defend the fact that we have these good accuracies so that we can then ship those out and then monitor how the models are performing in production. So in practice, the data and machine learning in practice involves looping through these 5 processes until you have a deployable solution. So we first try to understand the domain, prior knowledge and goals. What is the domain we're working on? What is the, how much data prior to this do we have? And what is the goal? Are we trying to classify fraudulent actors, or are we trying to predict something else? The next is we try to do data integration, selection, cleaning, pre-processing. Data integration, selection, cleaning, and pre-processing just is what data do we have current? Where is that data seated? Where is other data? Can I get all that data in? So we're talking to data vendors, we're talking to third-party organizations. For instance, for a loan, for you to take a loan, the credit bureau has to send us some information regarding any possible loan you've taken in the past so that we can know, who you are. That now comes in as a data point for you. We have to find a way of pre-processing it. We have to find a way of integrating it to the model we're working with. We have to find a way of arranging it such that it makes sense in trying to predict if you will default. So that process alone is a whole task that can sometimes span up to months in getting all that data in. But once you've gotten it in through data engineering techniques, you can then successfully build the kind of systems you want. Learning models seems to be like the shortest possible or the easiest task we would actually have, since we know, okay, it's this particular problem, we just jump on some particular algorithms, and when we can get a good learner, we know why and how the model is performing, then we can settle to either engineer our own models to solve those problems better, or if the chosen learner is good enough, then we just go ahead with it. Next, after we've built the models, we have to interpret these results. The model will give us results. We find a way to interpret these results to stakeholders. So CBN would want to know, how are we deciding who to give a loan to or not? C-level executives would want to understand, how is your model predicting or doing what it's doing? And there has to be reason behind it, right? There has to be some kind of reason behind it. For the deep learning models, right now, there's a lot of noise on why we can't use deep learning models, even though we're seeing them working. And one of the reasons is because of interpretability. But the truth of the matter is we are seeing new ways now of interpreting deep learning models. So very soon in almost all domains, you would be seeing a lot of AI, deep learning methodologies being used. Because people are now beginning to trust the systems, trusting how the algorithms are learning. And yeah, it's a bit scary, but yeah, people are beginning to trust the methods better these days. Once we've been able to interpret the results, we consolidate and deploy the discovered knowledge. Consolidating and deploying the knowledge means, okay, fine, you have a model, you've built it, you see that it has some very good confidence. What do we do with that model? We've accepted that it should work. We now have to find ways of deploying the model. And in deploying the model, I mean, we make it available for people or the target audience to interact with it. So if it's a credit scoring model, we just plug it to an application form so that when you come in through an application, through an app, you can apply for your loan on the application, and the credit scoring model will tell you all the information you need there on the app. If you're trying to chat, the text generation model will be able to tell you the next the next word predict the next word you're trying to talk about, you're trying to say. If you're trying to get recommendation, you would get recommendation because the model is facing your application or is being connected to the application and you're interacting directly with it. So I don't need to have an office where you come into the office and try to fill an application form or anything. You can just fill it on an application or on a website, and the model gets to see the inputs you give and can process those inputs and send back a response to you without me even knowing. All I'll just be at the back end is monitoring stuff. So we have to find the right platforms to deploy the models. Some of them can be very large in size based on training, and some of them can be quite small. So we have to find the best systems to make sure it is available for you to use in terms of speed, in terms of space, and all of that. Do we deploy it directly to your application, to your phone, or do we keep it somewhere and just point our application to it? So all of those, we have to think about those systems and yeah, the best ways we can have those models out there. So I have mentioned a lot of technical terms, a lot of technical terms that I feel you might have issues with, or that anybody would have issues with understanding. Feel very free to outline them, send me a mail, send me a DM, anything. Just ask questions on what I talked about. And if you need me to do another video call or something to explain deeper to you, I will be really glad to do that. Right. So in conclusion, machine learning and classification in general is very easy. The only difficult or the demanding process in it is understanding and mastering it. Daily we see new techniques, daily we see new methods, daily we see new data, and yes, you understand what classification can do or doesn't necessarily mean you can solve every classification problem out there. It now means that you have to spend time learning. You have to spend time learning about a particular problem. And just when you're about to get the hang of it, a new problem comes out. You have to learn about that one. Or just when you're trying to get a hang of that one, another problem comes out. It's that consistent movement, that consistent migration from learning solutions that makes it just a bit demanding. Learning the best tools to use, learning the best methodologies that could be used for a particular solution. And yes, if you have any solutions you are thinking of and you don't particularly know how to go about them, you can reach out to me. I would help with drawing out a roadmap for how you can actually deploy, build that solution from beginning to end, and give resources that you could research for that problem. So one has to basically learn the basics of the trade and build up from there to more sophisticated solutions. What helps you scale through is an understanding of the foundations. If you understand the basics of linear algebra, calculus, programming, and data structures, you would most likely be able to build on that. Once any new solution comes out, you're able to understand what it does and relate to what it does, and also think up your own solutions such that you can solve problems in that area or using that particular method. So the solutions listed here are non-exhaustive, and many more still emerge daily. So our lives are spent in front of screens. We're always reading papers. We're always reading mathematics textbooks to understand how stuff is done. It's not easy, right? So it's a bit demanding, but at the end of the day, it's actually quite rewarding, because if you come from a solution perspective, solution driven mindset, you would find that being able to solve some of these problems that affect thousands of people, if not millions, on a daily basis, can be very rewarding. Can be very rewarding. Think about the solutions Google gives in AI. Think about the solutions Facebook gives in AI, and think about how rewarding the engineers must feel in those areas, knowing that they're in those companies, knowing that their solutions affect literally the whole world, literally the whole world. So I encourage anybody who is interested, go into machine learning, go in now. Like, go in now. You don't have to have a PhD. You don't have to have a master's. You don't even have to have a BSc. You can learn machine learning at any level, at any point. You can understand the techniques. You can start from a developer perspective and just build systems, and then start understanding how those systems work. And then from there, go to the math, go to the deep stuff, and pick up why they work. So you learn how they work, then you pick up why they work. And with that, you will be able to solve almost any problem you come across in machine learning. So thank you very much for attending this or being available for this. And like I stated at the beginning, my email is on this slide. I'll be giving it up to. My Twitter handle is also there. You can send me a message anytime, send me an email, formal email. There's the formal email address. I'll just go to the top again. And yeah, you can send me a formal email requesting assistance or help with something, or you can send me a hangout mail. I love hanging out. But sadly, due to the COVID-19 situation, we'll hang out online till we can do that more in person. So yeah, thank you very much for attending this. And if you have any questions, just drop them down.
Right, awesome. Yeah, thanks for the session. I think it was very insightful, to be very frank. But go back to your first slide. Was that meant to be Ymail or Gmail? That's your
Ymail,
Hangouts.
Ymail.
Oh, Ymail. Oh, okay.
Yeah,
Impressive. Oh,
yeah.
okay. That's awesome. So, guys, thank you so much, everybody, for attending this session with Vangelis. Like, if you can text Vangelis, if you can text him or anything, we had a podcast show with him, so that should be released by next week, and you can follow our social media pages to see when we release the podcast with him. It was very, very insightful. In fact, quite lengthier than this, and had a lot of body of knowledge and encompassed in such conversation. And I'm so glad we got to do this with Evangelist. So, if you have any questions, this is you're most likely going to be watching this in the viewing party. Drop them in the live chat. If you probably missed the live chat for some reason, of course you can text Evangelist directly, email Evangelist directly, and of course follow him on Twitter as well. And we'll see you next week again. And it's still on, just a teaser if you made it this far. Next week's session is also on classification yet again. And of course, with I think an alumni of AMISS, if I'm not mistaken, Evangelist. That's
AMMI.
AAM, exactly. So yeah,
Yeah.
that's Jerry Fagua, and such an
Yeah.
amazing person as well. All right, thank you so much, everyone, for attending. See you next time, and stay safe. Yeah.
Yes. Stay safe.